Thank you, Adrian, and good morning. I apologize, my Spanish is not great, so this will be in English. I'm Vice President of Development at Solar Reserve, also responsible for origination and power marketing to the mining sector. Just a little background on Solar Reserve. We're a leading concentrated solar power, or CSP, project developer. We also do photovoltaic PV projects. We have more than 3 gigawatts of CSP projects in development globally. And our lead project is a 110 megawatt project that's in commissioning in Nevada, Crescent Dunes, which I'll talk about a little bit more. Late last year, we were also awarded a second project, a 100 megawatt project in South Africa called Redstone. That's reached a soft financial close. Financing is underway now, and construction will start on it later this year. And then we also have late-stage development opportunities around the world of more than 1,000 megawatts of permitted projects. So a pretty robust pipeline. And then on the PV side, we've been very successful in South Africa, especially in the first 2 rounds of the Renewable Energy Independent Power Producer Program. We have 246 megawatts in operation currently there. We've also secured 7 power contracts in the United States, and another in Central America, in El Salvador, as part of a competitive tender. It represents about 175 megawatts peak of PV capacity. And then we're very active in more than a dozen other countries on the PV side. So taking those independently, those CSP and PV projects, we've also developed a hybrid concept where you develop combined CSP and PV projects to provide higher capacity factors at a lower LCOE. And I'll talk a bit more about that since it's applicable to Chile. So we are a traditional developer, but you should also think of us as a technology company. We have very differentiated technology that we own and have acquired. It's mainly related to what you see here in this picture, which is the receiver that sits atop the tower. It's thin-walled tubing in a high heat flux environment with very special alloys and metallurgy, and it's based on rocket engine design. So we literally have a dozen or so rocket scientists that are on the engineering team at Solar Reserve that are improving the technology. So this gives us the solution in solar energy to operate day and night as a baseload facility and to compete with conventional generation sources. So as I mentioned, our most recognizable project is our Crescent Dunes project. It's our flagship project. Located near Tonopah, Nevada. It's a former, I believe, silver mining town, halfway between Reno and Las Vegas. Was basically an abandoned town for the most part, so it's provided a lot of beneficial economic development now and needed revenues to that town. The project is designed as a 110 megawatt facility with 10 hours of full load storage. And the way to think about the 10 hours of storage is if we don't recharge the hot salt tank, we can operate at full load for 10 hours before we wouldn't be able to produce electricity any longer. So it's really 110 megawatts times 10 hours or 1,100 megawatt hours of storage. The project is designed to produce 500,000 megawatt hours annually. So if you compare that to PV, it's more than a 2x output. This represents more than I think it's a 52% or so capacity factor. And we do have a 25-year power purchase agreement with NV Energy, which is the largest utility in the state of Nevada. So just briefly, how our storage technology works. What we do is we capture sunlight and concentrate it from a field of heliostats to the top of the tower where the receiver sits. Liquid salt from the cold salt tank that you see there in yellow is pumped through the receiver where it's then heated to 1,050 degrees Fahrenheit or approximately 566 degrees Celsius, so very hot. That heated salt is then pumped down the receiver and placed in the hot salt tank, so that's where the storage occurs and allows us to release that salt on an as required basis to dispatch the plant, as however it's designed. That hot salt is then pumped from the hot salt tank through a steam generator to create steam at high temperature, high volume, high pressure, that then drives a conventional steam turbine. And this is the same type of steam turbine that you would see in a coal or nuclear plant. It's not a solar turbine that requires lower pressure, so it's utility grade. So then that cold salt, after going through that process, flows back to the cold salt tank, and then this process is repeated day after day after day to provide the continuous output. This is an aerial view of Crescent Dunes. We're very near complete construction. I'm not sure what the 0.2% left is, but it's nearly 100% complete. Commissioning is in advanced stage, more than 80% complete. And we have a COD target of this July 2015. So it's an exciting time because this represents the commercialization of the first of its kind in this technology, so scaled up to a utility scale level. Oops. This is just a zoomed in look at the Crescent Dunes power block. So we have, as I mentioned, the conventional steam turbine generator, the air-cooled condenser, hot salt tank, cold salt tank, steam generator system, water treatment facility, and molten salt receiver. So it's a very compact design, and what you'll notice here is we only require 2 tanks. Many other types of CSB technology, say trough with bolt-on storage, require 4 or 5 times the amount of salt to store the same amount of BTUs through their process. This is a nice photo looking down the main access road. So you get to see you can see the scale of the heliostats. Those are the facets on the back that you see. They're 115 square meters each, so almost the size of a billboard. They're quite large. And as you'll see on the receiver, this is initial heat flux through the commissioning process where we're directing sunlight from a portion of the solar field onto the tower. So this is part of the commissioning activities. So I have a video now that's drone footage that's pretty interesting to watch. If you guys could cue that up. Actually, that one. It's okay. So that's a good video. A video's worth more than 1,000 words, I think, in this case. So there's been a lot of talk about intermittency from PV and wind and matching that to a mine's load. This is a pretty simple chart. We've got a PV or photovoltaic system here on a typical time of day scale for a representative day in California, where everybody recognizes that there's intermittency from those two. What's very unique, and I can't stress this enough about our technology, is that we can provide a firm block of power customized however the customer wants it. So in the 8-hour generation profile, which is a taller profile, we would add a larger steam turbine to produce more megawatts in a shorter time period. We can also do a 16-hour generation profile or a base load 24-hour profile. So in certain markets where there's a peak pricing or a time of day, we can take advantage of the higher pricing, say in the afternoons. The Crescent Dunes facility is designed to come in the late afternoon and all the way past midnight to feed the load in Las Vegas. So they specifically, Nevada Energy specifically wanted us not to operate in the morning. So it's a very unique PPA in that respect. So, really the point here is that we're able to shift our electricity generation to meet different profile needs. So in terms of mining companies, we think there's a high applicability of our technology to serve, base load mining loads. Certainly mines need reliable 24-hour supply. Oftentimes for off-grid mines, they have a lack of grid services characterized by high energy cost. And so I'll stress that our facility can be grid-tied or off-grid, so we can be completely remote as the sole source of power. We may need to add in a little bit of diesel backup just for periods of low solar insolation, but it's a marginal addition. And of course, the other interesting thing about mining and solar is that where most solar companies operate, there's a strong overlap with where a lot of major mining operations are. So, Mexico, Chile, of course, southern Peru, South Africa, Western Australia, which has a very high avoided costs because of expensive diesel, and parts of Asia. This is just a chart that's meant to show the correlation between mine load and how our hybrid system would interact. On the top, you have a fairly flat, consistent mine load in gray. The orange represents when you can produce PV, obviously during the day. That's also the time that we collect thermal energy in a CSP plant. So this represents somewhat of a PV output and CSP collection profile. The green on the third would represent a somewhat typical CSP output if we're only dispatching the CSP. It's fairly flat, but we do have periods of seasonality where our profile will drop somewhat. The yellow then represents the molten salt storage level that's in the tank. As we're drawing down that salt, of course, we're releasing BTUs, and we have to fill that back up, and that's directly correlated to the CSP output as it's dispatched. And so finally, on the bottom, a hybrid system, when it comes to a PV CSP system, is really the integration of PV with CSP. The basic idea being PV would run during the day, and CSP fills in around the shoulders, and of course at night, to provide that continuous 24-hour supply that matches the actual mine load. Furthermore, we are able to guarantee the output level to any customer and provide generation guarantees. So we will not necessarily ask the customer to take solar resource risk because we're confident enough in being able to design a system and a minimum guarantee level that can satisfy their mining requirements. So here in Chile, we have a very aggressive development platform, 800 megawatts in development, roughly split 400 megawatts in the SIC and 400 megawatts in the SING. This is our lead project, Copiapó, which is a hybrid project. It's two CSP towers, approximately 130 megawatts each, integrated with 150 megawatts of PV. It's being designed to operate 24 hours daily, continuous operation. Of course, we have inherent storage, which makes it 100% dispatchable. The capacity factor on this is in the 92+% range, just to put that in perspective. And then on the annual output, we've correlated satellite data to on-site data, and our current projection is more than 1,850 gigawatt hours of production, which is a tremendous amount of energy that can be produced. If you compare one tower at Copiapó to the 500,000 megawatts at Crescent Dunes, and keep in mind this is the exact same design, we will produce approximately 40% or more energy here in Chile from the same configuration. That's entirely due to the stronger solar resource. So if ever there was a place for our technology to be deployed, it's in Chile. The field diameter is about 3.2 kilometers per tower. Water use is roughly 200,000 cubic meters per year. That's for the whole facility, so 100,000 per tower. The other important point is that we don't require any natural gas as backup. We run entirely from the solar resource, and so that means there's no air emissions. And furthermore, because it's a solar resource, there's no fuel risk to a mining company, so we can completely hedge that risk for a customer. So this is a photo and rendering of our three of our projects in South Africa. The Lesedi PV project and the Jasper PV project, those are operational PV projects that I mentioned earlier. Redstone is the 100 megawatt CSP project that we were awarded at the end of last year. That will start construction this year. So in essence, this represents the first hybrid PV CSP solar park in the world. So we're very excited to be leaders in this area. So when finished, it'll look very similar to this rendering. Back to Copiapó, just to give you a sense of the output band. This is a time series for a few days in August and September. And the blue represents the PV being operated at 150 megawatts, and then the red is the CSP. We do operate within a band, but the band is held pretty tight. So in this case, at Copiapó, we expect to typically operate at 220 megawatts and within a band of 200 to 260 megawatts roughly. So we'll be able to control that band. Obviously, if a cloud comes over the PV field and the PV drops off, we'd hit that lower band. So that represents that bottom graph in the blue where you have the inverted triangle. That'd be a cloud cover. So we're doing a lot of studies and proposals for mining customers, and have done a number of renderings. So this gives you an idea of a rendering that we did for another client and how a CSP PV hybrid system might look next to a mine. And then finally, I'll just close. I have one more small video, which is an animated video of this rendering. Okay, thank you.